to talk about low voltage diagnostic. Once we break it down, it's actually pretty simple. It's looking at this huge package and then trying to understand how the individual components work. And everything is really coming down to relays, contactors, electrically controlled switches that allow the flow of electricity, and that flow of electricity controls different components in the system. Relays make the world move. They're in everything that we do, from our cell phones, our zoning panel, our thermostats, the control boards on our furnace, even those big relay stations that make sure that there's power flowing to everything in our home. It all comes down to relays, and relays provide control of the current so that we can ensure that the power is going where we need it to go. They take many different shapes and forms. Some of the ones on here were more common in the HVAC industry, so we're a lot more familiar with them. That one in the lower right corner, that's very common for truck stock to have one of those for humidifiers. The brown one there on the right side, it's not quite as popular today, but a fan center relay for a boiler system or a really old furnace that didn't have the control boards that we have today. It was a relay that plugged into the fan center socket, and that's what gave us our control of the HVAC equipment. So relays are in every part of our industry, and they really haven't changed as far as operation goes. They've just changed in appearance. A relay is an electrical device that incorporates an electromagnet activating a switching signal that allows the path of electricity to flow. So it provides isolation, it provides control. What's the difference between a contactor and a relay? For what we do in the HVAC industry, the only difference really between a contactor and a relay is the amount of current it's designed to handle. The contactor is typically designed for greater than 10 amps. The relay is typically designed for less than 10 amps. We got a lot of different types of relays in the industry, but the ones that we're most familiar with in the residential light commercial are the SPST and the SPDT, single purpose single throw or single purpose dual throw. And more commonly, that relay on your truck is probably going to be a SPDT, a single purpose dual throw. So that coil controls a single set of contacts. Now you might have the DPDT. It's not quite as common. That usually we're going to run into those more with the industrial controls. You have your coil. Your coil controls a single lever that bounces back and forth with a spring keeping it at the B side of things, and then you energize it and the magnet pulls it towards the A side of things. So on the SPDT, we have a normally open contact, which is A, and we have a normally closed contact, which is B, so NO and C. Relays, from a cutaway, you can see that there's an armature with a spring. That spring wants to hold it in the normally closed position. However, once you provide a current to the coil, the magnet in the coil is stronger than the spring. And when we do that, it then pushes those contacts closed. So that's all we're really doing. We're using one input current to control a different output, and that provides us with isolation. What are we using relays for in the HVAC industry? The thing that we use relays for is control and or isolation. The control side of things allows us to have multiple things happen, multiple events, multiple conditions. Then as those conditions are fulfilled, the equipment's allowed to continue operating. On the isolation side of things, you have a humidifier or the Arzel panel. Perfect example. The Arzel panel has its own transformer. The transformer in the Arzel panel powers all your thermostats. However, your furnace has its own transformer as well. We cannot tie those two transformers together, so we have a bank of relays on the Arzel board that provide you your isolation. So your HVAC outputs on the Arzel panel are dry contacts. We'll talk about that a little bit later, but that is your isolation. It separates out the transformer that powers the panel from the transformer that powers your furnace, because we need that additional power for the thermostats themselves. If you tried to have, let's say, 4 thermostats on your furnace transformer and then power the zoning board with that as well, you'd burn out your furnace transformer before too long. It's just not designed for that current. So sometimes we need multiple transformers to provide additional energy, additional load rating. And that's where the isolation comes into play, because we don't want to tie 2 transformers together. Relays in action. We've got two transformers in this instance. One transformer is energized, which then energizes the coil in the relay when we close a switch. So in this case, there on the left side, we had that switch. We close that switch or we open that switch. And as we open and close that switch, the relay opens and closes its contact. Now the purpose in this case would be, we'll say the left side of that relay is a 24-volt circuit. The right side of it is a 120-volt control. So I have 120 volts flowing through my light bulb. I have 24 volts as my control source. So as I open and close that switch, I open and close the pathway for that voltage to power my light. What is the best way to test a relay? What's the best way to test the contacts on a relay? Ohm meter, resistance. The best way to test the contacts on a relay are to test your ohms. If I have a set of open contacts, what am I going to read? We'll read infinity, we'll read high resistance, we'll read OL, or possibly that little infinity symbol. And that indicates an open set of contacts. If I have a closed set of contacts, a lot of technicians listen for that beep, beep, beep on their meter, but that toning doesn't indicate the quality of contacts. So if I'm going to ohm it out, what am I looking for to say that that's a good set of contacts? 0 would be perfect. However, in an imperfect industry, we're actually looking for anything less than 1 ohm of resistance. So if it's less than 1 ohm of resistance, we know that there's not significant impedance. So that's as close to, probably the closest I have ever seen to 0 is a 0.02. And that's essentially just touching my meter probes together. So there is some resistance to our meters themselves, not significant. There is some resistance to everything. However, we're looking for less than 1 ohm of resistance, and that indicates that we have a good contact. So if we have an issue with our furnace not working and we've tested our resistance on a specific circuit, we read less than 1 ohm, we know that our problem is now somewhere else because that contact is proven. It's verified good. Sometimes we can't always test for ohms. So in those cases, we need to test for voltage. So if I have an open contact, I'm going to read 24 volts. And the reason I read 24 volts on the switch side, if I have an open contact, is because it's broken. One of those acts as the path to ground. The other one acts as my hot source. So if my switch is open, I'm going to read 24 volts across it. Now, I want to be careful there because I have to also verify that I've actually got 24 volts to there. So if I read 0 volts, that doesn't necessarily mean that my switch isn't closed. I want to verify that I've actually got 24 volts going to that set of contacts. So the reason I like to use the resistance, which we talked about earlier, is because the resistance will tell me definitively whether or not that contact is closed. If I'm reading voltage, I need to test a couple different locations just to verify that there is actually voltage present. If I can verify that there is voltage present, then a reading of 0 would tell me my contacts are closed, but a reading of 24 would tell me my contacts are open. So if my contact is open, I'm going to see 24. If it's closed, I'm going to read 0. But if I read 0, as I just mentioned, I need to test another point to verify I actually have 24 volts feeding into that contact. Because if I don't have voltage feeding up to that circuit, my voltage test isn't going to really tell me anything, but my resistance check would, which is why I like resistance over voltage. So if you are using voltage, make sure you test a couple different points, verify that there is actually voltage getting to that contact point. And once you verify that there is voltage getting to that contact point, a reading at 24 indicates it's open. Of course, if you read 24 volts, you know you've got voltage going there. However, if you read 0, that doesn't indicate that it's opened or closed unless you first verified that you do actually have voltage making it to that set of contacts. So 0 volts may be open, may be closed. You have to test again just to verify that you do have voltage going there. A reading of 24 volts indicates open for certain. When we start diagnosing our HVAC system, we always start at our thermostat. Now there's a lot of things that will tell us our thermostat is running. But if things aren't running, our thermostat's the place to start. And technicians, as they become more experienced, will be able to skip some of these steps. but it's good to know the basics. It's really good to go back to the basics, because when we have a compounding problem, we need to be able to know what is or isn't working so that we can diagnose as many of the potential failures as possible. A compounding problem typically means that there's more faults later on, and as we can test around the trouble that we found initially, we can then verify further points of operation that are causing us problems as well. So the place to start is with the thermostat. The thermostat is that starting point for all our controls. And just because the thermostat's calling for heating, just because it's calling for cooling, doesn't mean it's actually calling. And that's where we need to start our testing to verify that the thermostat is good. So in this example, it's pretty basic. We just have our RWYG O/B in common, and I have it drawn out with the relays for open. So as we start calling for things, we're going to see those relays change. So pay attention to the switches. I have a switch that's closed. What is this call if I have a conventional system? Heating. It is a call for heating. How about now? What's this call? This is a cooling call. Correct. This one's pretty simple. Fan call. The G contact is closed. But now we have a heat pump. There's something with the Arzel panels that determines what call this is from the thermostat. So looking at that with a heat pump system, thinking specifically Arzel panels, what is this call? So something to keep in mind with the Arzel panel, from the thermostat, doesn't matter what Arzel panel you are using, your reversing valve is always energized on a call for cooling from the thermostat itself. So when I have a thermostat, I have a heat pump system. If my O terminal from the thermostat is energized, that has to be a cooling call. Now, even if you have a piece of equipment where the reversing valve is energized in heating, you got ream root or something like that. Even though that specific piece of equipment requires a reversing valve energized in heating, from the thermostat, the Arzel panel always has the reversing valve energized on a call for cooling. And then through the panel itself, we control your reversing valve function to your equipment. So if you have the AirBoss or the MPS panel, the O terminal and the B terminal on your HVAC outputs are separated. So if you have the MPS or the AirBoss and you have a piece of equipment that energizes in heating, such as the ream root, then your reversing valve wire from that equipment hooks up at the B terminal, B as in boy. However, the thermostat still has to energize that reversing valve on a call for cooling. So when I look at this thermostat call and I think about the Arzel panel, the O/B terminal is closed, that has to be a call for cooling from the thermostat, because the Arzel panel is what controls your reversing valve. So then when I look at the reverse of that, my reversing valve terminal is open now. I know that's a call for heat. Now that we've finished with the thermostats, we need to start looking at the equipment. On a basic call for heat, my thermostat calls for R and W, the contact closes. And then from the control board on the furnace, it'll energize my vent motor. I have a 120 volt source that powers my furnace. I have my control board, which is 24 volt to my thermostat. My thermostat then controls my contacts. So on a call for heat, I close W. That then starts my vent motor. My vent motor operating closes my draft switch. So that proves that my vent motor is running now. With my draft switch closed, I'm looking to make sure that my limit switch is closed. And while those happen simultaneously, this is kind of a sequence of operations, but a lot of these things happen at the exact same time. The check is happening at the exact same time. And if any one of them fails, my heat does not run. So from my call for heat, my vent motor starts. My vent motor proves my draft switch. My control board also proves my limit. If my limit is open, it's not going to allow the gas valve to start. So if my limit switch is closed, my draft switch is proven closed, my gas valve is then energized. And then there's another circuit, the flame circuit, the flame proving circuit. We call it flame rectification. That determines that there is a proven flame. If there's a proven flame, a fan timer starts to give that heat exchanger a chance to warm up. Once that timer is complete, my blower activation relay starts and my blower kicks on. So when we start looking at it, our thermostat initiated the call for heat. And then we can see the dominoes that fall into place to actually make that heat run. So step one, we started our thermostat. From there, we prove it at our furnace. From our furnace, we make sure our vent motor starts. Make sure our draft switch, our limit switch, make sure that those are closed. If those are closed, our gas valve will start. If our gas valve is proven to flame circuit, it starts our timer, and then our blower starts, and we have heat. The steps are pretty much identical from one furnace to the next. It's just different configurations. So while it may look different because the furnace is set up differently, things are in different locations, it all operates exactly the same. We start with the thermostat. From the thermostat, we move to the furnace. From the furnace, we move to the individual components to see which ones are starting, which ones are not. And as we knock those dominoes down, we can prove what is or isn't working, and we can work our way through the system with relative ease once we go back to the basics. On a cooling call though, a cooling call always has to have a fan call with it, because your cooling call, the Y, really only controls your compressor, and it determines whether or not the furnace needs to run a high speed or a low speed blower, but it does not determine that the blower actually operates. Your G call still needs to be there. And with the Arzel panel, if the G call is not there, the panel will view it as an illegal call. Basic cooling operation, our G call comes in and that starts our blower. Our Y call comes in and that starts our blower on high speed. Now that Y call then goes to the outdoor unit. If it's a really basic outdoor unit, it may or may not have high pressure and low pressure switches. If you're low voltage source, everything starts at the thermostat. Step one, verify your thermostat. Check your voltages, verify. Check your resistance if there's no voltage there. That'll be a pretty obvious one in this case. But if you have voltage and things still aren't working, check your resistance, because that'll prove those contacts for you. So step one, we start at the thermostat. Our blower should kick on right away with the call for cooling, so that one's pretty easy to verify. The blower kicks on, we're good to go. We can move to the outdoor unit. Do we have voltage at the coil on that contactor? If we don't, then we need to back up. We need to take a look at the high pressure switch, the low pressure switch. We need to take a look and see if there's a break in that low voltage line. If we have everything operating inside, our blower kicks on right away, it kicks on at high speed. We know that the furnace is working. We know that the thermostat's working. We move to the outdoor unit. We're missing our voltage there. We have to back up because there's a break in that line somewhere. Now it might be a high pressure switch, might be a low pressure switch, might be a mouse, a weed whacker, a dog, a cat, some kind of animal chewing on the lines. We have to back up and take a look at that. But if it's there, then our compressor and our fan will start, as long as we got the high voltage present as well. Now that we've seen the equipment, now that we've seen how the thermostats operate, we need to add zoning to it. The zoning system takes multiple thermostats, applies a set of rules, and gives you your outputs. When we have the Arzel HeatPumPro, all it needs is a W input, and it'll provide you with up to 4 stages of heat, 2 stages of cooling on the outputs based on your configuration. So if you have an all-electric system, a heat pump with 2-stage electric backup heat, the HeatPumPro will provide you with 4 stages of heat, starting with first and second stage condenser, moving to first and second stage of backup heat if necessary, based on your leaving air temperature. So we can have thermostats all calling for different things: fan calls, heating calls, cooling calls. The Arzel panel applies a set of rules and determines what we're going to send to our equipment so that we aren't damaging our equipment with conflicting calls. When we look at the Arzel HeatPumPro, there's that line that says out. That line that says out tells you exactly what's going to your equipment. So for this one, I have it showing what you would typically see for an all-electric application with all 4 stages calling. We see W1, W2, Y1, Y2. So that's compressor, first and second stage, Y1, Y2, as well as first and second stage of our backup heat. We can see our blower running at high speed with air handler Y1, Y2, and we have that G call going to the equipment for the fan operation. We can see that it says zones 1 and zone 2 are being served. So that's in the lower left-hand corner of the screen. It says zones 1, zone 2, or 1, 2. It's not 12, that's zone 1 and zone 2. So we can see that we have those 2 zones being serviced. Their weight adds up to 100%. And one of the things with the Arzel HeatPumPro is that your weight percentage does not have to total out to 100%. It can be less than 100. It can be greater than 100. But with the zoning panel, we can have thermostats calling for opposing things. The zoning panel provides the rules that prevent opposing or conflicting calls from going to our equipment, and that allows everything to work together nicely. But we have our thermostats. Now, when we look at the zone panel, while we might not have all those same safety switches that you're going to have with your furnace, from like the draft proving switch and all that, those are all part of your furnace. But when we're diagnosing it, as far as the voltage is concerned, our thermostats are our thermostat, but our HVAC inputs, the zone terminal connections in the Arzel board, would be our equipment. In relationship to the thermostats, those zone connections would be our equipment. And then when we look at the furnace side of things, the HVAC outputs are a thermostat in relationship to the furnace. So your furnace has all its safety switches. The HeatPumPro and the AirBoss do have a high temperature and a low temperature protection built into them. So that's where we look at that line that says out. If it is listed on that output line, it is energized going to your furnace. We look at it where it says zones. That tells us exactly what zones are being serviced. If we don't see our thermostat calling listed in the zone box, that thermostat's not receiving its call. So when we start looking at how things are calling, we start at our thermostats. Step one, we verify that our thermostats are calling. From there, we move to the zone panel itself. We verify that the zone panel is receiving those calls. And then once we verify the zone panel is receiving the calls, we can verify the HVAC outputs. And while we don't necessarily have to go to each individual device to test it with our meter, we can turn everything on how we want it to work. And then we can go to the Arzel panel. The HeatPumPro has the screens that walk you right through your diagnostic. Tells you exactly what thermostats are calling, tells you exactly what's being outputted for. So if we start there, we get a high overview of what's happening. And then we can know that this, and this are working. But if we don't see it happening the way that it's supposed to be, now we can focus our diagnosis there. So with the HeatPumPro, we can view our thermostats individually, and we can focus on that specific thermostat, that specific set of zone connections, because that's our thermostat and our equipment, and we can see where our problem's at on that specific zone. So it might be broken thermostat wire, it might be a bad thermostat. Rather than trying to diagnose all 4 zones in our equipment at the exact same time, we break it down into individual zones. Each zone has a thermostat. Each connection inside the board, zone 1, zone 2, zone 3, zone 4, is our equipment in relationship to that thermostat. And then the zone panel tells us exactly what it's outputting for. And those outputs are a thermostat in relationship to our equipment. So we don't have to try and diagnose all 4 zones in our equipment at the same time. We can break each zone down individually, and then we can break the equipment down away from the zone thermostats themselves. So rather than turning a thermostat on, saying the equipment's not working, and then instantly condemning the Arzel board, we need to take a look and verify that the thermostat's doing what it says it's doing, and then see what the panel says it's doing and verify that as well. A heat pump adds an additional layer because there's a defrost board outside. Once upon a time, the defrost board would throw me for a loop, but then as I became more and more familiar with how low voltage circuits worked, the defrost board really isn't any big deal, because it's all about a low voltage source controlling a high voltage source. Where's your power at? Once you verified your power, you know that that part of the system is working. If it's not, then you found your problem. So you start at the beginning, start at your thermostats. From the thermostats, we move to the equipment. From the equipment, it should be pretty obvious that our blower starts. And then once we've proven that, we can now move to the outdoor unit, to the defrost board. And at the defrost board, we're going to determine, do we have our voltage out there? If we do, we need to see what's running. Did our contactor close? If it didn't, then we probably have a high pressure or a low pressure switch that's going to be open. There's really a lot to take a look at with the defrost board, but it's still all exactly the same. It is your relays, it is contacts, it is a low voltage controlling a high voltage source. And as we start testing for the voltage, we can start to knock things down to see where the problem's at. If our compressor and our outdoor fan or our condensing fan motor don't start, it might be a high pressure switch, it might be a low pressure switch that's open. Once we verify those switches, then we can move on to figuring out where the problem's at. So the defrost board applies some logic to it. That logic is going to determine whether we're running in heating or cooling based on what's coming into it. So from the Arzel panel, the thermostats are always energized and cooling on the reversing valve, but we'll control that reversing valve operation based on your brand of equipment through the panel itself. In this case, we're just going to say it's energized and cooling. So as we start testing our voltages, we can start to see what's happening. If our motors aren't starting and stopping, it's probably an issue with a high pressure or low pressure switch. Might be a problem with the capacitor. Those are things to look at, but it all comes down to verifying our voltage, verifying our resistance, checking to make sure that the control source is doing what it needs to do. And then if our reversing valve is energized or if it's de-energized, determines whether or not we have a call for heating or whether or not we have a call for cooling. The AirBoss is very similar to the HeatPumPro. We can have heating calls come in. We can have a cooling call come in. We can have our fan call. Our thermostats are just that. They're a thermostat. From the thermostats, we move to the panel. Each zone connection is our equipment in relationship to that individual thermostat. And then from there, our HVAC outputs are the thermostat in relationship to our equipment. So we start at step one. We turn our thermostats on. Once our thermostats are on, we then go verify that the board is receiving that call. If the board is not receiving that call, then it's either a broken thermostat wire or it's a bad thermostat. So we would then have to look and see why is my thermostat or why is my board not receiving that call? And that would be voltage testing up at the thermostat itself directly. Do we have the voltage up at the thermostat where it needs to be at? If I pull my head off the wall, my thermostat head off the wall, do I have voltage between R and W? Do I have it between R and Y, R and G, R and O, R and C? If I have voltage between R in each of those terminals, then I need to look and make sure that none of my connections, W, Y, G, O, are potentially shorted together. But if those check out good, there's no shorts between W, Y, G, O, and I have voltage between R and each of those wires, then I know my thermostat cable's good. My problem has to be with my thermostat itself. But if I don't have a good voltage check from those wires, if I don't have a good resistance check to tell me that I don't have anything shorted out, then I know that I have a problem with my thermostat wire and I can proceed from there. Now, the Arzel panel is really simple to work around just to verify operation, because if I take a jumper wire and I jumper R and W1, that's a call for heat, or with the HeatPumPro, it's R and W. If the panel receives that call and everything works, yes. So on this image, there are two thermostats in heating, one thermostat in cooling, one thermostat and fan. That's to show that you can have thermostats with dissimilar calls, but the panel plays the coordinator. And as a coordinator, it determines what takes priority, heating, cooling, or fan. Doesn't matter what panel of ours you have, fan is always the least priority. So we pick between heating or cooling based on your operation. So if your thermostat is calling for heat, the other thermostat's calling for cooling, you can set a priority between heating cooling calls and it will serve that priority. With the HeatPumPro, you have heating priority, cooling priority, zone weight priority, or auto. With the AirBoss, you have auto, heating, or cooling because there's no zone weight. Automatic is first come, first serve. So if my heating call comes in first, it's served for 20 minutes and then it'll switch to the opposing call. The panel will never output for heating and cooling at the same time. It will only ever output for one or the other, opening or closing the zone dampers appropriately based on whether it's serving that heating or cooling call. With the HeatPumPro, there's individual zone screens that tell you exactly what's being received from the thermostat. With the AirBoss, there's an LED indicator for each of the zone connections. There's LED indicator on the HVAC outputs. So instead of the LCD screen that you have with the HeatPumPro, the AirBoss LEDs will tell you what it's doing. So looking at your zone connections, top to bottom, it's red, red, yellow, yellow, green, yellow. That tells you W1, W2, Y1, Y2, G, and O. And then across the top where the HVAC outputs are, it's red, red, yellow, yellow, green, yellow. That's W1, W2, Y1, Y2, G, or green, and reversing valve O, yellow. So we start there. We verify that each thermostat's calling. We verify that the panel's receiving that call, and then we verify our outputs. So we start at the thermostat moving to the equipment, thermostat to zone panel connection. And then from there, we started another thermostat, HVAC outputs, and we move to our equipment. Once we start verifying those calls, we can determine what is or isn't working appropriately, and then we can break that down into something that's more bite-sized, more understandable. So instead of trying to wrap our head around 4 thermostats, we can focus on one thermostat at a time, verify it's doing what it says it's doing, verify the board is receiving it, and then we can move to the next thermostat. And then once we verify that one, we move to the next. Once that's verified, we move to the next. And once those are verified, we now move to our HVAC outputs, which are a thermostat in relationship to the equipment. The panel is going to have several diagnostic lights on it. It might be first and second stage heating, LAT, might be compressor lockouts. So the panel does have indicators to tell you that it's got something disabled. There's reasons for it. And if you're confused when you're looking at it in the field, reach out to us, tech support at arzelzoning.com. So G, Y, and W, if you notice, so your question is zone 1 thermostat has closed, G, Y, W, is it in heating or cooling mode? But if you notice at zone 3, it has Y, G, and O closed. So if you remember back to the thermostats, O is always a call for cooling when you have a heat pump. W, Y, G closed is a call for heat pump with auxiliary heat. So this would actually be an all electric application. You have your heat pump, your thermostats are calling for the compressor, and then you have one stage of electric backup heat, W, and your thermostat determines it needed to call for the auxiliary heat. Now the AirBoss, if you want the best control of multi-stage equipment, you need to use 2-stage thermostats. It does have built-in board timers. Not as huge a fan of delay timers as I am of letting the thermostat control the staging. The HeatPumPro is a little bit different because it controls your staging itself, and it does that with just basic thermostats. However, the AirBoss, your thermostat matches its application. So if you have a heat pump system, use a heat pump thermostat. And in this case, WYG is a call for heat pump with backup heat from the thermostat. YGO is a call for cooling because the O is energized. So with all the Arzel panels, you can never energize from the thermostat O and W at the same time. That would be an illegal call. So that O terminal is what determines whether it's heating or cooling. And if it's a heat pump application, O is open, it's a heating call. If it's a heat pump application, O is closed, it's a cooling call. And you can never energize O and W at the same time coming from the thermostat, because the panel will view that as an illegal call.